the pleasure to have Beth Biller with us from the University of Edinburgh. And she will tell us about combining astrometry and direct imaging targets. You have 35 minutes.
All right. Well, good morning to those of you here in California. Good afternoon, evening, or middle of the night to those of you online. And thanks, Jackie, for such a fantastic introduction to the topic of directly imaged exoplanets. So I'm just going to try to pick up where Jackie left off. Here, of course, no direct imaging talk would be complete without a gallery of all the pretty planets, right? So we've all seen this system, HRA 799, Beta Pic B, kind of the OG directly imaged planets, and newer discoveries from GPI and Sphere, the first custom-built planet imagers. So recap. The sort of planets we're detecting right now are what I like to refer to as baby Jupiters. So masses of greater than 3 Jupiter masses, effective temperatures from 600 to 1400 Kelvin. So they're very hot. They've just formed. Usually, well, ages of less than 100 million years, which is not young for normal people, but for astronomers, that's young. And we're looking at them via their thermal emission in the infrared. The ones we're detecting right now are from tens to hundreds of AUs from their star. We hope to move in closer, obviously, in the future, and detected at a factor of 10 to the 4 to 10 to 6 contrast. So most of this work so far in terms of detection has been in the near infrared using 8-meter ground-based telescopes plus adaptive optics plus chronography. So lots of kit and lots of post-processing techniques. But as I'll show you, Gaia really opens up some new parameter space for these in terms of characterizing them. So what do we know about them right now? So Jackie discussed the L and the T spectral types. So these objects start out hot and they just cool monotonically with time, just like their somewhat more massive cousins, the brown dwarfs. They move through the L type. So this is where you have thick silicate clouds in these atmospheres. And as they cool, they transition to the T dwarf type, where the silicate clouds have broken up and dropped below the photosphere. So this is the main structure we see on this color magnitude diagram. The L's here and the T's here. But one key difference that we're seeing between the directly imaged planets, so the objects with masses, estimated masses in most cases less than 30 Jupiter masses versus say 60 or 70 Jupiter mass field brown dwarfs, is that the directly imaged planets, low mass brown dwarfs, are redder than their field brown dwarf compatriots here. So here are, for instance, some of the HRA 799 planets. Some of these free-floating planetary mass objects, they're very red. And this is really pointing towards these silicate clouds in their atmospheres. In fact, while we expected these objects by their luminosities to be T dwarfs, they've turned out to be L dwarfs. And only one of the directly imaged planets we know to date is actually a T dwarf, so a slightly cooler object. And this is 51 Arri B right here. And it's the only one that has this methane absorption feature at 1.6 microns. That's indicative of basically a clear atmosphere and slightly cooler temperatures. All right. So why do we need additional techniques when studying these objects? So we can look at their colors, but the masses for most of these are estimates from models, right? So estimates from models that have not been fully tested, especially at young ages and low masses. So while we have lots of information from the photometry and spectroscopy, to really fully interpret these, we need a dynamical mass. Otherwise, we estimate masses in this very circular way from models that we haven't tested with real masses. So combining photometry plus spectroscopy plus a real dynamical mass constrains these models, helps us better characterize the objects that we can't yet determine masses for. Unfortunately, we can't do this with direct imaging itself. So I am contractually obligated to show this video as part of a direct imaging talk. And we all love this, it's great. And I actually love it in particular because it's such an excellent demonstration of Kepler's third law. I show this to undergraduates, honestly, right? So Kepler's third law is A cubed is proportional to P squared, right? So you can see this really clearly. Our inner planet here with a shorter semi-major axis clearly is zooming around there, moving much faster, has a shorter period than our outermost planet B, which is moving much more slowly further out, right? So Kepler's law, just looking at it right there. Now, unfortunately, Kepler's third law gives us a proportionality between semi-major axis, period, and the total mass of the system, right? So just the total mass. So with direct imaging alone, you can only get the total system mass. If you'd like to actually get the masses for the planets themselves, then you need to combine with another technique, right? So we have two choices here. We have radial velocity, and we have absolute astrometry. So absolute astrometry in this case, we have just basically, if you don't have a companion, your star will move in a straight line on the sky. If you do have a companion, it will tug it a little bit so you can see a very slight deviation. And obviously this is not something I really need to tell this audience. You're really quite familiar with this idea since we've had a couple talks about it already. So combining with radial velocity, here is our one characteristic equation for radial velocity. This is the radial velocity semi-amplitude. So we just have, our constant g, our period, sine I, the inclination to the system, the eccentricity, our total mass, and the mass of our secondary. So with just radial velocity, you have your sine I uncertainty. We don't, once you combine that with direct imaging, that takes care of sine I, and then the combination with radial velocity gives you M2 as well. So this is one path you can take. The other, of course, is absolute astrometry. So there are a few different parameterizations of this. This is from Makarov and Kaplan, 2005. Delta mu is the deviation essentially between the straight line of the motion if it was just a single object from the little tug on the star due to the secondary here. So this little bit here is delta mu. This is parallax here. Again, semi-major axis, total mass, the mass of the secondary, and this R naught is essentially dependent on the orbit. So eccentricity, and this big E here is essentially just telling you what phase of the orbit you're in. So for a phase on orbit, this becomes an equality, but the basic point here, without going into too much detail on the maths, is that like with radial velocity, we have this M2 explicitly in the equation. So if we combine with direct imaging, we can then get both component masses. So putting this all in one slide, you have your choice. You start with direct imaging, you can combine with either radial velocity or absolute astrometry or both. And that's the way you can get individual component masses within a system. So the combination with RV has come a bit earlier than the combination with absolute astrometry. So about a decade ago, we saw the first detection of substellar companions from their RV trend. So this is from Krepp et al. 2014. Here is an RV trend around the star HD 19467 caused by this imaged brown dwarf companion. So you can use this to detect new objects. You can also use this, as we just discussed, to essentially determine the full orbit of the system. So this is a more recent orbit determination of the brown dwarf GJ758b, combining direct imaging and radial velocity. So here is the direct imaging astrometry and separation and position angle across several different instruments. Here are the radial velocity data. And then you can use an orbit fitting code such as Orvara. And I think this is kind of the precursor of Orvara that was used here to determine the orbital parameters. And because we're combining two techniques, radial velocity as well as direct imaging, here we get the constraints on the mass of the companion here. And over here is the best fit orbit here, as well as about 100 orbits drawn from the posterior PDF as well. So this is RV plus direct imaging. You can get even stronger constraints if you add in Hipparcos and Gaia information. So this is from Kalissendorf et al. 2018. They took the posterior PDFs from Bowler et al. And what they did is taking orbits from those posteriors, they essentially estimated what measure, well, from the models, looked at the observations with Hipparcos and Gaia and looked at which of the posterior models from the RV direct imaging combinations could explain the Hipparcos and Gaia astrometry here. So here are the full set of simulated orbits, and here are the accepted orbits overplotted now on the astrometry points. So you can see comparatively, these two authors chose different angles to show this on, but oh well. Comparatively, this has improved the orbit. So this was the first example of this I could find in the literature. There may be some before, and I apologize if I missed anyone's work. Please tell me if I have. And just a little note about what we're fitting. I kind of already said this, and actually Tim said this in his excellent talk, talking about all the details you need to think about when you're doing this. What we're actually fitting, we have the epoch by epoch relative astrometry. We have the epoch by epoch radial velocities, but we don't actually have the epoch by epoch Gaia astrometry right now. We won't have that until data release 4. So what we're actually doing is taking model orbits, predicting what the proper motion would be given the actual observations, and then comparing it to the Gaia proper motion or the Hipparcos proper motion or the proper motion anomaly, and doing it carefully, for instance, using Tim's catalog of accelerations that has thought about all of the systematics you need to take into account, especially when combining Gaia and Hipparcos. Okay, with that note, let's continue on. So there's a lot of results for both brown dwarfs and exoplanets. And as we know, the boundary between the two are porous. I'm going to focus on the lower mass contingent, the younger contingent, because Myrick is going to talk about the brown dwarfs in the next talk. But there's been kind of a flurry of these measurements since 2018. I'm not entirely sure why 2018 was when this started out. I'll just highlight the first and the last of these. So beta pic B. So yeah, really classic planet. Now we think it is about 12 or 13 Jupiter masses, and kind of like a higher mass analog of Saturn. It's about 10 AU from its star, but quite a bit more massive, but also around a more massive star. So here is the best fit direct imaging orbits, radial velocity, and Hipparcos and Gaia constraints from Dupuy et al. 2019. A very similar paper, so I'm kind of balancing between two different papers here. Stellan and Brown did very similar sort of analysis, and from their analysis, here is their constraints on planet masses. So the green box is the constraints from direct imaging on the orbital period of the system, and their Hipparcos Gaia constraints are here. So they found a planet mass of about 10 to 12 Jupiter masses, so an actual mass, not just, oh, we estimated from some models that are not very well constrained at young ages. And another one I'd like to highlight is one I've mentioned earlier. So 51 Ari B. So this is the coldest imaged exoplanet to date, the only T-dwarf exoplanet we know of. And of course, we see this beautiful methane absorption feature. And very excitingly, we recently have dynamical masses for this as well. So this is from Dupuy et al. 2022. So here are our direct imaging constraints on the left, our constraints from Hipparcos and Gaia on the right. And you get essentially a measured mass from these. So on the right, on this plot here, are the 1 sigma here and 2 sigma masses that come out from this set of the best orbits, 100 orbits drawn from the posterior. It puts the mass of this is quite low, so probably less than 5 Jupiter masses. Now, the interesting thing about this is everyone likes to say, okay, it's a T-dwarf and it's a bit closer into its star. So, oh, this must be a cold start planet, right? So we think of planets as having 1 or 2 formation mechanisms. Well, actually, there's probably a lot more, and it's very hard to form wide planets to begin with. But we think about planets as either having a cold start formation mechanism where you have basically a solid core and it starts accreting gas. And those tend to be fainter at young ages compared to hot start, where you have an instability in the disk and it collapses very quickly. And the interesting thing about this is that comparing with the model masses and what we have here, I never explain this axis here. This is the initial entropy, right? So how puffy the object was to begin with. We expect over here, the puffier objects to be hot start models. So essentially what this has said is that we can actually rule out a fair chunk of cold start models compared to the measured mass. So not necessarily a cold start planet. Okay, so I've shown you examples where we've very clearly been able to divide our orbits into here's a primary star and here's a companion, and we fit everything, and we clearly get a nice result where we have one companion. What happens if there are additional companions in the system? So sometimes you get a really weird result. This is a recent paper looking at two M-star binaries. So the primaries are early M's and the secondaries are mid M's. And this is, I'm not going to show you the orbit fits for this. I'm just going to show you kind of the summary plot where for one target here, we have a model mass estimate from its luminosity of about 100 Jupiter masses. However, the dynamical masses turned out to be a lot higher. And then the second system that we looked at in this paper was pretty much the same, right? So whether you looked at the dynamical mass or a model mass, it was the same. And these are stars. So our models are not quite so uncertain. They're main sequence stars. So it should work out well. So this is basically saying, it looks like we have more mass in the system than is accounted for in the luminosity. So our best explanation for what happened here is that there's probably an additional companion in this particular system. So if this system consists of an early M, a mid M, and then we have a cheeky T-dwarf companion of maybe 30 Jupiter masses, that 30 Jupiter mass T-dwarf is really faint compared to our two M stars. It can be hiding in the system and give us this additional dynamical mass component without being detected. So there's a couple of cases like this. I think there's actually down the pike very soon a new planet detection from another system that showed a little bit too much mass in its dynamical fit. All right, moving on. So yeah, PowerPoint suggested this lovely image, and I just, it has actually very little to do with this talk, but I just went with it. Let's flip the problem. I've been showing you cases where we know of a directly imaged exoplanet, and by adding in astrometric information, we can constrain the orbit, get the dynamical mass. But can we just flip this the other way? Can we use astrometry to tell us where to look for new directly imaged exoplanets? You're probably, from the way I've posed this, the answer is, well, yes. All right, so again, multiple approaches to this problem. Multiple groups are working on this. So I've been trying to balance the contributions of these different groups. If your group is working on this and I've missed you, let me know. I want to make sure that give everyone credit. So 3 methods that are overlapping but a bit distinct. We have proper motion anomaly, the delta mu method, and looking at instantaneous accelerations. And I'll give a very brief overview. This one, I think Pierre is going to talk about this a lot more in his talk, so we won't go into this in too much detail. And Tim mentioned this in his talk yesterday too, which is between Hipparcos and Gaia, we don't have 2 measurements of proper motion, we actually have 3. So we have the the measurement of proper motion over, I'm not supposed to move out of here because you can't see, okay. Over the lifetime of a given mission. So here, if you measure during the Hipparcos epoch, this is what you would see due to the motion of this binary. If you measure during Gaia, this is what you see. You can also look at the difference in positions between Hipparcos and Gaia and get more of a long-term proper motion. So this is mu Hipparcos Gaia. And if you look at the difference between either the Gaia or the Hipparcos one and this long-term one, so this equation here, you'll basically be able to detect the tug of an unseen companion this way. Similar method, so I discussed this already, so just parameterizing this delta mu, we can use this equation from Markov and Kaplan to measure it too. So, and in this case, we are essentially considering the difference between this proper motion here and one of the more instantaneous ones as this delta mu measurement. And you can use this essentially, if you have a signal, if you measure a delta mu, then you obviously just from itself have a degeneracy between a close-in stellar companion versus a further out planetary mass companion. So that's what we're looking at here. So this is the range of values that could explain the observed delta mu for this particular test case from Fonte and Neve et al. 2019. And then you have a prediction for where your companion is. If you look at it with a variety of direct imaging missions, you can try to detect it and you expect it to be somewhere along here. And if you don't, so if you you have this signal and you look at it with sphere and detect nothing, then you have constrained it to be quite low mass. You know the signal is here. Okay, and the last technique, which Tim talked about yesterday, so I'm not going to go into in any detail, is that if you have both direct image, Hipparcos Gaia and RV, you can just go back to F equals MA basically, right? So that's what this is. So we have in the plane of the sky, in the tangential plane, and here is our projected separation. Just combine these and you can solve for the mass. So this is another method. Okay, so now I'll transition on to talk about results using these techniques. And this has actually been really in the last couple of years that we started to see objects detected via astrometry and then picked up via direct imaging. So this is a white dwarf companion to the star GJ4436. So here is the delta mu expectation plot. And here is where it was actually found. Here's the image of it over here. Very soon after that, we have a brown dwarf companion that was detected as a companion to a sun-like star. So here is the discovery image with SkexAO. And here is an orbital fit combining the direct imaging and the astrometry. As you can see, we can get pretty good constraints on, for instance, a mass of our secondary, even with actually not a whole lot of, so just a few orbital points here from direct imaging and Hipparcos and Gaia. So this is really powerful, especially if we're really after the dynamical masses. And very recently, several groups have simultaneously detected a brown dwarf companion, the first brown dwarf in the Hyades. So here I'm going to try to balance between three different papers. This was detected simultaneously between Kuzuhara et al. 2022, Bonavita et al. 2022, and Franson et al. 2022 is a characterization paper that is going to soon be submitted. So here's the prediction on the sky of where the planet should be, and it's right where it was expected. So it's also, we can see from its spectroscopy, quite low mass. So this is sphere spectra here, and it fits quite well with this T1 spectra standard, as well as a young L9 as well. And of course, why are we doing this? We'd like to not just fit models, well, these are actually standards. We want to compare dynamical masses to model masses in order to eventually refine these models. And here we have dynamical mass versus various model masses. So they overlap, but the dynamical mass is actually a bit smaller. So this is actually really key. And what we're going to see in the next few years as we have more of these dynamical mass measurements for lower mass objects, is this will be pushing refinements in these models, which is going to be a key for understanding the ones we can't get dynamical masses for. All right. So not only are we starting to see single results, the first survey using these techniques has recently been published. So again, this is the same sort of plot giving from the measured delta mu signal, comparing, in this case, TGAS and Hipparcos, Gaia DR2, where we expect to find the astrometrically detected companion. Here is the contrast achieved with sphere in this case. And this is just one example case here. These are the 10 new binaries detected in this survey. And 4 of these are brown dwarfs, and the rest of them are stellar binaries. So this has a very high yield, right? So if we've done blind surveys in the past for directly imaged exoplanets, where we choose the youngest stars that we can find, so members of these young moving groups and young associations that Jackie was talking about, And we've just kind of blindly searched, just going to see whatever we can find there. And what we learned from those is that young planets are rare. From those blind surveys, for every 100 stars surveyed, we maybe would find one companion. This survey, in comparison, looked at on order 20 stars and found 10 companions. So the yield is really high. Now, the thing is, if you have this kind of signal, you can have it can be a stellar binary as well. It may not be a low mass companion. So that is one thing to note. Another really cool thing that's come out of this survey, so this is online, this really fun tool, this really cool tool called Forecast. So this is using the information from Gaia and Hipparcos, from the proper motion anomaly, but we also we have proper motion in RA and proper motion in DEX. So we understand what direction the tug on the star is coming from. So we can make predictions as to what part of the sky, what direction we expect to find the companion in compared to the star. And here were the predictions from Bonavita et al. 2022, and here's actually where they were found. And you can see that this prediction tool really nailed the positions of these companions. So if you have a star that has Hipparcos and Gaia astrometry and has a delta mu or a proper motion anomaly or whatever, acceleration, however you want to call it, and you'd like to get an idea of where your companion may be sitting, try out this tool. Okay. So I have ended up talking very, very quickly. I guess we'll just have lots of time for questions. One last thing I wanted to touch on. So we're going to see a lot more surveys looking at proper motion anomalies, at delta mu, at accelerations. I'm expecting a lot of discoveries in the next few years, a lot more dynamical masses. But we're still kind of looking at these young baby Jupiter planets. So higher mass planets around young stars. Now, in a few years in Gaia DR4, as we've heard, we expect to find a lot more planets, right? So thousands, although I guess we haven't been able to pin down an exact number yet. We'll find out. Now, the next question is, are we going to be able to image these new planets from Gaia DR4? So they're going to be primarily closer to their star. And given that most of the stars in nearby, well, most stars are old, what that means is, yes, we will be able to detect some, but maybe not so many. So what you have on the left here, these are simulated Gaia planets from Perryman et al. 2014. So a full simulation of the expected yield of Gaia, and we're going to find out really soon how well this corresponds to the actual yield. And then this contrast curve here is a prediction for the PCS imager for the ELT from 2010. It's basically one choice, but is fairly interchangeable with predictions for similar instruments on other ELTs. So of the thousands of planets, we're going to be able to directly image a few dozen of these. But as we've seen, combining the techniques is really powerful. We'll have dynamical masses for these, and because we have direct imaging, we're going to also have atmospheric information on them. And in comparison, here on the right, this is the cohort of known RV planets just taken from the exoplanet encyclopedia and compared against the same contrast curve, a similar yield of RV planets with ELTs. All right. I'm going to just put up my conclusions. I apparently talk really, really fast when I'm in front of people and nervous, but I think takeaways from this, we really need dynamical masses to fully characterize exoplanets, especially because we're looking at things that don't have a main sequence, right? They just cool monotonically with time. So we tend to just take an age, estimate mass from a model. We need that age to be really good for that to work, but it's better to really pin down those models with dynamical masses. We have to combine direct imaging with another technique to get individual masses. And the choices we have are essentially absolute astrometry and radial velocity. But to be honest, in most cases where you have a dynamical mass for an exoplanet, is actually the combination of both. We can see that looking at Hipparcos and Gaia measurements, we can pinpoint hidden planets and brown dwarfs. We've had the first direct imaging detections with this technique, and we expect quite a large yield of these objects in the next few years. Thanks, everyone.
Thanks, Beth. We have good time for questions. But is there anything online?
My question. So this question's asked, what forecast tool do you use? The forecasted results amazingly agree with observation. Would you please explain a little bit more?
Okay, the tool itself is called Forecast. So this was put together by Mariangela Bonavita. She presents it in her recent 2022 paper. Mariangela, you have the link for this, right? So we can circulate that. So what was that again?
Mapstar. Yeah, could you please put it in Slack?
Yeah, we'll share it gets put on the Slack.
And we do have another question coming in, asking, are there any interesting trends about the host stars with the newly discovered brown dwarfs?
I'm not sure what was meant by interesting trends there. Like in terms of radial velocity trends or?
So it's asking, are they mostly intermediate mass, low mass?
I see. Trends in the mass of the star. No, actually, I would say. So if you look at direct image exoplanets as a whole, what you'll find is that higher mass stars do seem to have more planets and higher mass planets, and that reflects what's been found for radial velocity planets as well. In terms of trends with the set of newly detected objects that have been detected via proper motion anomaly, it's probably too early to say. A lot of them are higher mass brown dwarfs. And actually, there is no published exoplanet detection via this technique yet. I think in a couple of years, when we have a few of those, then we might be able to say something about whether there's a trend with host mass. And I would probably expect it to follow the same trend that we've seen for other directly imaged exoplanets.
Stars that haven't been observed with Hipparcos but have been observed with Gaia, is there anything we can do astrometrically now, or do we need to wait for those full Gaia data in DR4 to come out?
Yeah, it probably needs to wait for DR4. Part of the issue is when we're looking at directly imaged exoplanets that are further from the star, we really need that long time baseline. So we're really leveraging the fact that we get a 25-year time baseline by combining Hipparcos and Gaia. I would think we know when we're getting to Gaia DR3, DR4, DR5, when you're getting past 5 years, there may be some information you can glean on closer in planets, especially around nearby stars, that might be directly imageable. But I think with directly imaged exoplanets, the longer the astrometric baseline you can get, the better.
And there's no way to use like ground-based measurements as well. It has to be the like Hipparcos and things that are much more precise from the space.
For directly imaged exoplanets, yes. For some of the higher mass brown dwarfs that are brighter, there are some options for combining in ground-based imaging as well. We're looking at one brown dwarf binary, actually, where we found it's in our plate library, and there's plates from like the 70s and 80s, and it's bright enough. It's a very nearby binary that actually we're looking at how to combine the plate astrometry with Hipparcos and Gaia, but I think that's a pretty rare case, unfortunately.
Thank you.